Great. Well, it's a real privilege to be here, and I appreciate the opportunity and the invitation to come and talk to you. I'm a little bit of a neophyte to the scene, and so what I'll be talking about, I don't have my own company yet. So you'll actually hear a little bit more on the preliminary side of how things are going, what lessons we've learned, and the mistakes we've made, as well as the successes we've had. I chose this title because it's just about the most vague title I could think of that still was accurate. We'll tell you a little bit more about what our technology is, but won't dwell on it too much. You'll also notice that I'm a adjunct professor in several departments, not including chemistry. I wish I could be a part of that crowd and be as cool as the organic chemists down there, like Ryan, but we can all dream. So what we do without immunoassays? Probably most people in this room have either experienced an immunoassay or directly done it themselves, or at least some of their samples have been sent away to labs like RUP for an immunoassay. And what these assays do, they tell us how much of something is there, or if something is there or not. But there's some problems and real limitation with these. And so I put together a really simple kind of conceptual idea of how these things work and where we saw kind of an unmet need. So if you look at this, what you do for a basic immunoassay, and what's represented here is ELISA, is you start with a whole bunch of signal. You have an antibody that's trying to bind to your target to tell you if it's there or not. And it's just flooded the whole system with a signal. And then what you have to do is wash out the unbound fraction. And eventually you'll be resolved down to a point where you can distinguish something, okay? And obviously this is you're not trying to see if you have a U in your blood, but the idea would be that you'd be able to distinguish if something is present or not and how much of it is there. Now, the problem with this is a lot of times when you do this kind of a wash, you didn't get it all the way. You have background noise, right? And so you have this kind of a system where, yeah, you can identify that something's there, but the signal isn't nearly as strong as you would like it to be because of this background noise. And the reason that is because the signal's always on. From the beginning, it's there, and you have to remove whatever unbound fraction you have. Well, we really wanted to come at this a different way. What if we could have a system where there was no signal until it bound? So the signal's off, and then turns on. And so the way we came up to do this was using antibodies, hence the title, antibody-based diagnostics. And what we decided to do is hijack another system that's out there using split enzymes. And in our approach, what we have are two different, cool. Nope. So in our system, we have two inactive fragments of an enzyme. These white pieces at the top look like half of an egg. And then they're both attached to an individual protein binder, an antibody. Once these both bind in the presence of the antigen, they refold the enzyme complex and give a signal. So conceptually, it would look like this. At the beginning of your assay, you have no signal. And then, as you slowly, the signal then appears. You don't have to do any washing. The only place that you have a signal, the only location, and the only thing that gives you a signal is the presence of the antigen and the binding of the antibodies. All of that unbound fraction doesn't fold up to give you the signal. So it really facilitates how fast we can detect a protein, also where we can detect a protein. So instead of being limited to things that we have to hold on to and then wash everything else away, we can just do this directly without having any kind of washing steps. And so where the story started for us is we conceptualized this idea, and the first thing we did was thought, hey, we're pretty smart people. Let's go and figure out what kind of assay we need to do. And in my own personal experience with working with breast cancers, I thought, oh, well, HER2, this is a breast cancer marker that's important, and that there's diagnostics, and let's go and do it on that. And we did. And what we found as a result is that we can detect HER2 in serum at a concentration that's about 10-fold lower than the commercial test that's out there. And so we're really excited and very naive, thinking that this was our hook to get into a diagnostic realm. So the first thing we thought is, okay, we defined our tech assay value, and we wanted to find people who really cared. And so we went to pathologists, and we said to them and to other people that we talked to, we have a novel idea. This is a beautiful, sexy idea. And we're going to detect HER2 with it. And it's comparable to the gold standard. It works, it's faster, a little bit faster, a little bit more sensitive than what you have out there. And our response was surprisingly negative. Nobody was interested. People said, why would I change? Why would I want to do this when I already have a gold standard? I barely use that one that much. It's because it shows my own ignorance in what was really important in the field and what was important to those people, what was their pain point. So kind of taking a step back, it was a kind of a simultaneous pursuit. We contacted TVC, and we really wanted to come back and reevaluate this idea of what was important, who's going to compare about this platform technology, who our best customers are actually going to be. We disclosed our work, and then through the help of TVC, we came in contact with 7 different individuals and started to work to talk to them about what their needs would actually be. By far, the one that I think has been most successful, in my personal opinion, is our work with Noriko, that you'll hear from a little bit later at ARUP. And we took a very different approach this way. We walked in and said, here is a platform technology. How do you think it could work for you? And we had this pretty cool little brainstorm session. I actually throw this up here. This is the actual whiteboard from our brainstorming session. And we came up with 4 or 5 ideas. They said, if you could do it on this system, it would be useful. So we took a step back and found that we could re-identify our application, what would be the most useful for it, and talking to labs that actually cared, what they would really use it for, not just because I thought it was cool. We looked at what we could actually build, where the assay components were going to come from, and what would the real deliverable be. What we were defining as an improvement was just the sexy, right? But the real improvement had to be faster, cheaper, more sensitive, or really meet some need that hadn't been met before. So after we've streamlined this technology we call target engaged complementation, now we have a new set of value to propose. And really, what we can do now is we know that we have a platform that's versatile. It's customizable to soluble or cell surface proteins. It's rapid. The total assay time's 30 to 60 minutes, and it's a single step. So it's homogeneous assay, eliminates multiple steps. So with this in hand, now we have a very defined set of tools that we go and say to this platform, what can we do with it? And then we could seek funding. Prior to this, we sought funding and were rejected ceremoniously, probably unceremoniously. But now I think the most important thing is, what lessons have I learned as a young academic going into the entrepreneurial field? One is what I think as an academic might be a good idea, what even might get funding from an academic granting agency does not necessarily mean it's a good commercial idea. I would tell everybody, get to the clinic and identify the nail long before you start working on your hammer. And the last thing I would say is disclose early, way before you think you should, to avoid some of the situations that were referenced in the panel earlier. This idea where suddenly I was caught in a very short time period needing to finalize a disclosure, a patent disclosure, before I was on stage presenting my work. And it put us in a very bad situation. So with that, I'm actually going to get us back on track a little bit. I really like to thank the people that have contributed significantly. This is my lab. We just showed up in Fano one day. It was amazing. And the main collaborators that we've worked with, especially Noriko Kuzukawa, you'll hear from her in just a minute, as a panel member. She's outstanding, an amazing individual, and very supportive. Julio Delgado is another member of the RUP community. They've been extremely supportive of us and really given us kind of the drive and the direction that we needed. TVC, Lina Bhatti, she's been great as well, really from the very get-go, kind of guided us in navigating this entire a maze of entrepreneurialism. And it continues to be supportive as we file our patents and move to the full commercialization. So hopefully next year I'll be able to come back and tell you about the small startup that we have and the $2.5 or $5 million that we've raised to commercialize the product. Thanks.